Right, real quick. Picture I'm done. Other foot.
Okay.
I will text you when we're pulling up. How about that? And see if it sounds good.
Okay, this is solutions to week number 5. Recorded at home. Okay, problem 1. We are told that a plus b plus c is 0 and a squared plus b squared plus c squared is 1.
Yes.
Okay, so here's how I would do it. I would say that ab plus ac plus bc, you can find it like this, right? It's a plus b plus c squared minus a squared plus b squared plus c squared, which is 1/2 of that. So it's minus 1/2. Then let's square this. We get a squared b squared plus a squared c squared plus b squared c squared plus twice abc, a plus b plus c equals 1/4. Now this is 0 because the factor a plus b plus c is 0. Therefore, we can conclude that a squared plus b squared plus a squared c squared plus b squared c squared is 1/4. Okay, and then after that, let's see. We just say that a to the 4th plus b to the 4th plus c to the 4th plus twice this thing, a squared b squared a squared c squared plus b squared c squared equals a squared plus b squared plus c squared squared, which is 1. Therefore, this is 1/4. So therefore, we solve for a to the 4th plus b to the 4th plus c to the 4th equals 1/2. Okay, so what could go wrong? Some of you knew a lot about symmetric functions and wrote some identities, but you always run a risk that the grader will say that this is not a common knowledge, you should have proved it. So everything is so short and so elementary that why not just write it explicitly like that? Some of you also had a very long solution, which was unnecessarily long. I mean, it was still correct, but there's always a chance of irritating the grader. If a problem has short solution, the grader might try to pick on a longer one if you give him a chance. So that's not good. Okay, but still, many people solved it, so it's an easy problem. Let's see. Let's move on. And yeah, I do recommend reading up a little bit on symmetric functions. It's a nice thing to know about mathematics. Okay, so let's do problem number 2. If I can erase this. Okay, problem number 2. So we will just write the following: that k plus 1 plus k plus 2 plus etc. all the way to L is the same as summing all the numbers up to L, which has a sum, and subtracting all the numbers up to k, which has this sum. And then this you can simplify as 1/2 L minus k, L plus k plus 1. So at this point we can state the answer. So the answer is the only numbers. So and the only requirement we are told is that it shouldn't be just one number you're summing, which means L minus k is bigger than 1. So the answer is that you cannot write like this powers of 2. And those are the only numbers. So first of all, you cannot write 1 like that, which is easy to check. Now, the there are two things you need to show for this problem. First, you need to show that you cannot write like this powers of 2. And second, that you can write like this any other number, which is not power of 2. So both of those are important. If you didn't do one of those, if you just showed that you cannot write like this powers of 2, but you didn't explicitly argue that you can write like that every other number, then you solved only half of the problem. Okay, so why can't you write powers 2? Well, those two numbers over here have different parity. Therefore, one of them is odd. The only positive integer odd divisor power of 2 is 1. It would have to be this guy, because this guy is strictly bigger than this guy, and the other divisor of power of 2 is strictly bigger than 1. But as we know, this L minus k cannot be equal to 1. Therefore, therefore, powers of 2 cannot be written this way. Now, assume we have some number which is not a power of 2. So write our number m as a power of 2 to the q times some odd number r, where r odd. And we are assuming that r is bigger than 1. Then there are two cases to consider. First case is basically which of those two factors is bigger. And if 2 to the q is bigger than r, then we solve system 2 to the q equals L plus k plus 1, r equals L minus k. And if it's the other way around, we solve system r equals L minus k, 2 to the q equals L plus k plus 1. And now the system always has solution because r is odd. And the only thing we want about k is that it's greater than or equal than 0. So k0 is still okay. So, and for that reason, you just, and we know that this number is strictly bigger than this one or the other way around. And it's easy to see that it always has a solution. And the solution will always have L minus k not equal to 1 because we assume that r is bigger than 1. Okay, so this always has solution, which means all numbers different from powers of 2 can indeed be written in such form. Okay, this was problem number 2. This was problem number 2. Yeah, you may need to take him. Okay, problem number 3. Let's do problem number 3. Something is very bright on the whiteboard, but I guess there's nothing one can do about it. There's some way to shield the window, maybe, or
No, but maybe I can block the glare.
yeah. Okay, problem number 3. We have a square A, B, C, D.
No, I don't think there's anything. Sorry. Can't help.
Yeah, maybe put it.
Just move it a little. So
Yeah, let's just move it. Okay, so we have square ABCD, and we are told that there are points K and L on those sides, so that those two segments are equal. And then we draw BL, and we drop a perpendicular AM onto it. And we ask to find this angle, KMD. Okay, so here's how I did it. There are other solutions. Let's just also draw AL. Then this angle AMD is equal to this angle because this quadrilateral is cyclic. Why is it cyclic? Because two opposite angles are 90 degrees, right? So AMLD is cyclic. Therefore, AMD equals to ALD. However, similarly, if you draw this line KL, then this is 90 degrees, just because this is a rectangle, say. And then AKML are also cyclic, and then angle KMA is equal to angle KLA, which is this angle. And therefore, you see that those two angles together is the same as angle KLD, which is 90 degrees. So the answer is 90 degrees. Okay, I don't think this problem was super hard. Also, some of you wrote that two of triangles here are similar or obtained from each other by some kind of spiral rotation without really giving any argument for that, which you cannot do to give argument for everything. Okay, so let's see, let's do number 4. So number 4 was doable just by bashing, apparently. So the original version where I got it said you had to prove it for any power of 2 numbers, not just 16. So, and then of course you cannot do bashing. So how do we do that one? So you remember there are 16 numbers written up to A16, and then so actually let's just say 2 to the k numbers written. We will do it by induction on k, and then in one move you replace them by numbers A1, A2, A2, A3, all the way to A2 to the k A1. And then you repeat it, and you want to show that after a finite number of moves, it will always become 1, 1, 1, 1, 1. Well, I think that so the trick is just to repeat it 2 times, and you will see that on the next step you will have A1, A2 squared, A3, A2, A3 squared, A4, etc. But square of plus minus 1 is always plus 1, so you can just get rid of those. So you and then you see that what you have is A1, A3, A2, A4, etc. But those are just same kind of thing done to 2 separate subsequences, right? You can think of odd numbers here, A1, no, sorry, not here. You can think of A1, A3, A5, etc., and you can think of A2, A4, etc., all the way to A2 to the k. So this is a step of induction, right? So we are proving by induction on k that for any A2 to the k such numbers, you always get 1s. The step of induction is that if you just apply transformation twice, it's the same as if you applied it separately to each even number and each odd number. And each of those forms a family of size 2 to the k minus 1. So that's why you do. That's how induction step is done. So you just repeat pairs of procedures for each of them, and by induction you're done. So the only thing we need is a base of induction, and well, the base, let's say k equal 1, in which case you have A1, A2, A1, A2. And on the next step, you have A1, A2, A1 squared, A2 squared, which is just 1, 1, 1. So the base is easy, and the step is done just by observing that applying a step twice is the same as applying it separately to 2 to the k minus 1 elements of the even index subsequence and 2 to the k minus 1 elements of the odd index subsequence. Okay, this was problem number 4. So I think those of you who did it by just bashing found out that actually they become equal to 1 much faster than it would happen if we use this inductive argument, I think. But it doesn't matter. You just need to prove that they become equal to 1 eventually. Okay, problem number 5. Okay, so not a hard problem, but surprisingly many people sort of screwed up with little details. So if we are told that x plus, let's see, 1 over y equals y plus 1 over z equals z plus 1 over x. So for example, we can take the first equality and we can rewrite it like this. X minus y equals 1 over z minus 1 over y is the same as 1 over yz. And then here's y minus z. And similarly, we can get y minus z is 1 over x. Let's see, xz, z minus x. And z minus x is equal 1 over xy. Let's see, x minus y. Now, multiplying them all together, we get that x minus y, x minus z, y minus z is equal to 1 over x squared, y squared, z squared. And then the same thing, x minus y, y minus z, x minus z. I might have somewhere changed signs, but I did it even number of times. Okay, so this was the first tricky point, because what's tempting is to just say that we can cancel those factors out, but for that you need to know that they're non-zero. And the problem, you are told that not all numbers x, y, z are equal. So this is again something I warned you about before. Not all of them equal means that there are two distinct among them. It doesn't mean that all of them are distinct. However, in this case, you can argue that, and you need to argue that if two of them are distinct, then all of them are distinct, right? So for example, if y is equal to z, then this 1 over y is equal to this 1 over z, and therefore this x is equal to this y. So if two of them were equal, they would all have to be equal, which we are told is not the case. Therefore, those two products are non-zero, therefore we can cancel them out, and we get that x, y, z squared is 1, therefore x, y, z is equal to plus minus 1. You cannot see here. So we conclude that x, y, z is equal plus minus 1. So many of you didn't do this step. Like you need to rigorously argue why you can cancel out this factor. And if it's not clear what this meant, but not all of them are equal, although I think it is clear, it just means that not all three of them are equal to each other. It doesn't mean that no two of them are equal to each other. You still need to err on the side of caution and argue that if not all of them are equal, if at least two of them are different, then all of them are different. Okay, so this was the first mistake some people made. And the second mistake is that once you arrive to this result, that x, y, z equals plus minus 1, you actually need to argue that this can work, that there are such solutions. You are asked what could be the value x, y, z. What if one of those plus 1 or minus 1 cannot be achieved? Then you didn't solve the problem, or maybe both of them cannot be achieved. So to make sure that you got the correct answer, you also need to provide an example or some argument that both of those are possible, which is not super hard. I mean, I think if you just assume that z equals 1 over xy, you see that x, if you let x be, let's see what, minus y plus z, that in terms of y it turns out to be equal to this. Then this for any y, this triple forms a solution. And if z equals to minus 1 over xy, then similarly you find that x equals y minus 1 over y, and z equals 1 over 1 minus y is a solution. So the point is that, or you can just plug in some particular number. You can plug in y equals 1/2 or something, and you'll get some triple of numbers here, triple of numbers here. But the point is you do need to argue that both plus 1 and minus 1 are possible, because you ask what are the possible values of x, y, z. You first argue that others are not possible, but you still need to argue that those two are possible. And some of you didn't do that. Okay, this was problem number 5. And let's do problem number 6 now. Okay, so let's do problem number 6. It's a geometry problem. Many of you solved it. You're told that you have two squares which share a common vertex, O, A, B, C, and O, X, Y, Z, where vertices are listed clockwise. And then you ask to show that AX, BY, and CZ intersect in the same point. So the cleanest solution I know of this is to do the following, to say, let's take the circles of those two squares circumscribed around them. They intersect obviously at point O. Let's pick the other point of their intersection. Right, let's let's call it this point, I don't know, P. And then we will argue that this point P is the point we want, right? So for example, let's argue that P lies on the line AX. Well, angle APO is 45 degrees because it's inscribed in this circle, and therefore it's equal to, for example, angle ABO, which is 45 degrees. And by similar token, OPX is equal to 135 because it's 180 minus or YX, for example, which is 45. So therefore, if this is 45 and this is 135, then points A, P, and X lie on one line. And similarly, it shows that B, P, and Y lie on one line. Here you could have two angles. One is 90 and the other is 90. And C, P, Z lie on one line because, again, you would have, for example, 135 and 45. So there's maybe a little bit of cases to consider in this problem, but I wouldn't take points off for that. But I didn't take points off for that. But that's the cleanest solution I know, sort of. Alternatively, you could first take point of intersection of, say, AX and BY and argue that the angle between them is correct, and therefore this point lies on those circles, and then you would use those circles to argue that it also lies on CZ, which is correct too. So this is, for me, the prettiest because it's sort of you first say that you find this point as point of intersection, the other point of intersection of those two circles, and then you just sort of kind of the same argument works for all three lines, that the three of them pass through this point. Okay, so this problem was just for knowing properties of inscribed angles and stuff like that. Although there are properties, there's this kind of spiral rotations, transformations, etc., which, if you know them, this is just a well-known property, but you cannot assume that. So if you get a problem like this, you need to actually argue it in some way without fancy knowledge. Okay, let's move on to the number 7. So number 7 was actually relatively easy, I think. Many people solved it. So 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9, 1/10, 1/11, and 1/12 are written on the board, and you want to erase as few of them as possible so that you can put signs plus and minus in front of the remaining ones to get 0. So as many of you observed, no matter what the rest of them add up to, let's call it A over B in reduced form, let's exclude 1/11. Then whatever the linear combination of the others is, B is not divisible by 11 because it's not present. This prime factor 11 is not present in all other denominators. And therefore, if you do plus minus 1 over 11, it cannot be 0. If greatest common divisor of B and 11 is 1. Therefore, we must necessarily get rid of 1/11s. And similarly, we must get rid of 1/7s. And then we can do similar thing with factor 5, prime factor 5. If we have plus minus 1/5 plus minus 1/10, no matter how you put signs plus or minus, you will still have something which has prime factor 5 in denominators. Therefore, you cannot get rid of it because all the rest of them will not have prime factor 5 in denominators. So you also must get rid of those two. And then the last two are 8 and 9. So, and if you remove 1/8, then all of the others have 2 to the power at most 2 in denominators. Therefore, the linear combination will have 2 to the power at most 2 in the denominator and cannot cancel with 1/8. And similarly, 1/9s. All the rest of them have 3 to the power at most 1 in denominator. Therefore, their linear combination would have 3 to the power at most 1 in the denominator. Therefore, it cannot cancel with 1/9, which has 3 to the power 2 in the denominator. So this one also must be removed. And that's so basically, yeah. So that's the argument, and then we are saying that so you need to remove at least 6, and then you can check that there is a way to put signs in front of the remaining ones. Let's see, -1/3, -1/4, +1/6, -1/12, so that this is 0. Therefore, 6 is really the minimal answer. Okay, so I think we kind of are using the following lemma. We are saying that let's pick some prime, and let's take maximal power of this prime, which appears in those denominators. Then we only allow this maximal power if it appears in at least 3 places, 3 different places. Because then there is a chance it will cancel out. If it appears only in 1 or 2 places, then there's no way it will cancel out. Therefore, we must get rid of those guys. Okay, so that was problem 7. So the answer is 6. We need to at least remove at least 6 of them by this argument, and on the other hand, we can remove 6 so that it works. Okay, and the last one was hard, although I think it was very pretty. So here's what we're going to do. We're going to prove it by induction. So this is number 8. We're going to do it by induction on the smallest amount of water in the jars. Right? So let's assume our jars have A less than B less than C pounds of water. Right? And we want to make A equal to 0. So we argue that we can reduce A, right? So you can do some pourings so that the smallest of them will become even smaller. And then, repeat it. Once it becomes 0, then we are all done. So how are we going to do that? So let's say we're currently in this situation where those are the 3 numbers. Let's divide B by A with remainder, right? So let's say B is equal to XA plus Y, where Y is a remainder, which means that Y is between 0 and A, and it's strictly less than A. I want to write X basically in base 2 in binary. In other words, I want to express X as this kind of linear combination, K1 plus 2 to the K2 plus etc. plus 2 to the KL. And it can be written in this way uniquely, right? As long as you require that, K1 is bigger than K2, bigger, etc., bigger than KL. Okay, so write number X in binary. And then here's what I'm going to do. I have my jar with A, and I have my jar with B, and I have my jar with C. So I'm going to take number A, and I'm going to ask, so A is A times 2 to the power 0, and I will ask, is 2 to the power 0 inside this representation or not? In other words, in this case, I guess I'm just asking, is X odd or even? And if X is odd, meaning that there was digit 1 at Z of X, then I will take B and I will pour A into this A, making this 2A. And if it was not there, if X is even, then I will take C and I will pour out of C A pounds of water into A, so that it still will be 2A. And then I will go to the next digit. So next I will think about 2A, which is A to the times 2 to the 1. And I will ask, was one of those numbers K over here? Meaning the last one now is the last remaining one 2 to the 1, or is it something bigger? If it's 2 to the 1, then I will take B and I will pour 2A out of it into 2A, getting 4A. And if it was not, I will use C. I will take C and I will pour 2A into it, making it 4A. So basically, that's what I will keep doing. I will pour A into here, then 2A, then 4A, then 8A. And each time I will do it either out of B or out of C, depending on whether this amount, A, 2A, 4A, etc., meaning 1, 2, 4, etc., do they occur or do they not occur in this presentation of X? So first, I claim that it's always possible to do it. Why? Because C is actually bigger than B. So therefore, if B still has more digits, then there's how do I say it? Yeah, well, if it's possible to pour something out of B, then it will also be possible to pour. I mean, am I saying it right? So the claim is that it's always possible to do it in a sense that there's always enough. So by construction, there's always enough of stuff in B, right? Because if the thing does occur in X, then it means that it's one of the things we add to get X. Therefore, X is at least as large as what we want to pour there. But it also always is possible to do if we need to do it from C, from the jar which used to contain C at the beginning. Why is that? Because we start with C being even bigger than B, meaning that the largest power of 2 which occurs in C is at least as largest power which occurs in X. So if we didn't cancel out still the largest power in X, then we still didn't cancel out the largest power in C. Therefore, it's still possible to do it. Okay, you need to be a little more careful with that, but basically you need to make such an argument that it's always possible to do it. And then basically for each digit in binary expansion of X, we pour out this digit into A, so eventually we will run out of them. So we'll run out of all of X, which means that in the jar which used to contain B, we'll just have Y left, the remainder Y, which is smaller than A, and that's it. That's our recursion or induction or whatever. Okay, I hope it was clear. So the only thing which was I was a little bit sloppy is why you can always do the pouring out of this jar. I think you just argue that still after each pouring, the amount of water in this jar is at least as large as in this jar. And how do you know that? Yeah, I think it's clear. So right, so anyway, you can think about it. I think it's an easy lemma, but you can think about it. So anyway, so this was the plan. Order the three things, divide B with remainder by A, and then use B and C to pour out into the jar with A, each time alternating so that you pour out exactly XA liters, pounds of water into A. And at the end, you will be left with Y. Okay, that was problem number 8. We are all done.